Hi, Bob here with JD Squared. In this video, we're going to be talking about K-factors. Now, what happens whenever you take a piece of metal, say for instance this bracket right here off of the markered system off XR12s or 6s, or you take a piece of tubing, whether it's round, square, doesn't matter. Anything that you're going to place a bend in, at the bend, let me get this one back up here, at the bend right here, it's going to either stretch, compress, like, shorten, or it's not going to do anything at all. Now, the odds of it not stretching or compressing are almost impossible. So, in order to determine how much it's going to stretch, we generally apply what we call a K-factor. Now, if you look at this tube, let's just say, for instance, when we bent this piece of tube or sheet metal, whatever, K-factors don't matter, but in this instance, we're talking about tubing. If we bend this and it doesn't stretch, in other words, the tubing doesn't stretch while we're bending, at the middle of the tubing, there will be no change. It didn't alter the length of the tubing. But on the inside of the bend, it would have compressed it, it would have squeezed it down, and on the outside of the bend, it would have stretched it. But somewhere between where it stretched and where it compressed, there is a line that didn't do either. It didn't stretch, it didn't compress, it stayed what we call neutral. That's the neutral plane. Now, typically, you're going to look at it and you're going to go, well, the neutral plane is going to be in the middle of the tubing. That's not the way it works in the real world. What happens in the real world is generally when you bend it, that neutral plane comes down. It lowers to the closer to the inside radius of the bent piece of material. So let's refer to this drawing I got right here, and I will be able to easily explain to you why it's so important to have the K-factor set correctly. Now, whenever you make a bend in a piece of material, you're not only going to need to know the K-factor, you're going to need to know the achieved centerline radius of the bend. So let's grab our tubing here just because it's a little bit bigger. Same thing for sheet metal though. The achieved centerline bend is typically larger than the die set that you use to bend it. So say, for instance, we used a 5-inch die to bend this. It looks more like a 4-inch die, but it doesn't matter. Well, if we bent that die, if you've ever bent tubing before or sheet metal, you've seen it spring back. It springs back out a little bit. So typically on tube like this is 1.5 inch tube right here. On that particular radius, we're going to get a spring back of about 1/8 of an inch. So even though we bent it with a forming die that was 4 inches, let's just say 4 inches, the achieved bend, where it actually bent, if we measured it, is 4 1/8. Now, the way you measure that is nothing more than a string, a nail, and a couple other things that you keep going around until everything's even. I could show you that in another video. In fact, I did. A while back, I did a video called Snake Therapy and K-factors. This is a long time ago. Well, the second half of the video will show you how to do what I was just talking about with the string and everything to determine the centerline radius of the bent after the material has been bent. Okay, so you're going to need those two numbers in order to create a part of the right size. So let's look at this drawing I've got in front of me here to explain why, if you have the K-factor wrong or the bend radius wrong, bad things happen. Now, first thing you need to do is tamp down your expectations a little bit. It's not a perfect world. So when you get a K-factor and a centerline radius and you go out on your bender and you bend everything and man, oh man, it worked absolutely perfect. Then a month later, you get some more steel comes in and this time you go out and bend it and the doggone the part's off by 1/16 of an inch. I'm just making up numbers here. That's probably because of the treatment, the heat treatment at the factory of the material. So for instance, I believe I'm correct, on tubing, mild steel we're talking about, welded seam, I believe the tolerance is plus or minus 11%. So you could go 11% hard, you can go 11% soft. Softer the material, the more it wants to stretch, that changes the K-factor. So what you're going to be looking for as you move through your fabricating process over the years is you're going to fine tune your bent radius and your K-factor until you're happy with the results. Do not expect perfection. Always add. A good engineer is an engineer that understands there are tolerances in this world and we have to obey those tolerances. So keep that in mind. But anyway, looking at the drawing in front of us, what I've done is I'm looking at a side view. It could be the side view of a piece of tubing, it could be the side view of a piece of sheet metal. It doesn't matter. When I mentioned earlier the neutral plane, that would be the red dashed line right here. That's at 50%. Right there. So if we bent that bend and we didn't have the tubing either got longer or shorter because of the stretch, then the neutral plane would be at 50%. The K factor would be expressed as 0.5. So a K factor is 0. We're on the bottom of the bend, the inside the bend. At the very top of the bend up here, the K factor is 1, 100%. Okay, so it's a 1. So let's look what happens if we make a bend and the K factor is lower than 50%, which it will be. You could take that to the bank. Let's just say in this case it's going to be 25%. Look at the distance right here. If we look at our red line up there, this one up here, that's the neutral plane, 50%. If we make that bend, we come up with a length of 5.4978 inches long. Here's the metric over here. Now, let's go ahead and say that the K factor for that piece of metal was really 0.25, 25%, right? It would have actually had a bent length then of 4.7124 inches. That's how long this arc is right here in the middle of this bend. Well, that's a difference of 0.7854 inches in that one bend. So now come along and multiply that by 3 or 4 bends in a roll cage or something like that, or a roll bar or a railing. You can see where you could be off 1.5 inches just because you've got the K factor wrong, or the bend achieved radius wrong. Now, in regards to the achieved or the centerline radius, the achieved radius compared to the K factor, the centerline radius is a little less important in the calculation than the K factor is. So generally, once I measure a bend using the string and nail trick, I told you about in that video, then what will happen is I will then generally fine tune my parts by changing the K factor. Because the K factor is the thing that's going to change more dramatically if you look at the heat treatment of the material, if it changes. The bend radius, yes, it is going to change. The harder the material, she's going to spring out a little bit further, but it doesn't seem, in our experience, to be as pronounced as the K factor does on the overall accuracy of the finished part, the length of the finished part. Okay, so you can see right here a big difference why you want to do that. Now, the way you test for a K factor, I'm going to show you that. We're going to go into Camelot, our design program, and I will teach you how to determine the K factor in that program. Okay, I've brought up Camelot right here. Let's go ahead and create a frame real quick. So I click Create Frame right there. Let's give it a second. Alrighty. Now over here on the left, this isn't a program to teach you how to use our software. We're talking just K factor, so I'm just going to zip through this. Let's go ahead and select the active profile. And right here, I've got 1.5 inch square tubing, 120 wall selected. Now, the K factor is 0.33 is what we determined at our machine. But let's go ahead and put it back to 0.5. Now, the reason I want it at 0.5 is whenever you create a new material to place into our profile library, it's going to default and set the K factor at the neutral, well, halfway up the tube, 0.5 inches, or 0.5, 50% of the way to the outside of the tube. So that's what it's going to do. Now, we do that because, as I mentioned earlier, it's always going to be below 50% or 0.5. I've never seen it get above that. So we use that number as kind of like a hint. So if I look and I see a K factor of 0.5, I know we've never checked it. That is not the right number. We are not going to get parts that are correct off of Camelot. So that's why we did it. But let's go ahead and save it at 0.5 right here. Remember that 0.33 is the real number. And let's make it active. Let's go over here. We're going to add a tube real fast. I'm going to add a point. We're going to make something simple. It's going to be that 1.5 inch square tube. and we're going to go up to 24 inches. Let's go another one. Let's make it 24 inches wide. Okay, notice it mitered it right there. We can go ahead and change that to a bend real quick. That's going to be the next bend, actually. This will be the miter. Let's change this to a bend. All right, let's go ahead and add another point. We're going to go here. Let me move this over a little bit. There we go. And on this one here, we're going to add a point. We're going to go back to the floor. Let's go to 0. And there we go. Let's apply and close. Okay, so there's our part that we created real quick. 24 inches tall to the middle of the tube. Whatever we design in tubing, most software, and definitely Camelot, we do not design to the, let me back up even more. We don't design, the height is not from the bottom of the tubing to the top. It's that bottom to the middle. And that's the center line of the tube. And most software that I've ever used is referring to the center line tubing when they're talking about height and width. So if you wanted a bar that was really 24 inches tall, you're going to have to subtract that 3/4 of an inch, which is half of the width of the square tube. I just want to throw that out there to you real quick. Anyway, we've got our part right here, and we're pretty happy with it. So let's go ahead and bend it. And there we go. But I don't actually want to bend it. I want to go to the Dimensions tab right here, click on it, and look at this length right here, 67.17 inches. Now, we know that's wrong, right? How wrong is this going to be? Which side? Do you think it's going to be too long or too short? It's going to be too long, because when your tube stretches in a bend, you've effectively added tubing to the piece that you cut. So this tube here is too long. So let's find out how much too long it is in this particular case right here. Did I say that right, or did I use bad grammar? All right, let's go back, and we're going to apply and close. And we're going to go back and we're going to edit the frame. So what I want to do first, if I go back and say I want to edit this, I'm going to go ahead and select the active profile, because we bent this, we went out, and we checked it, and our doggone part was too long. It was just too long. So let's change the K factor to 0.33, what it was before, and let's save it. All right. Now I'm going to show you a thing that Camelot does or doesn't do. Okay, so if I apply and close, you would think that since I changed the K factor, Camelot would have automatically adjusted that K factor. It didn't. Let me show you that. Let's go to Bend Selected Tube, go back to our dimensions, and there you go. 6.17, didn't change a doggone thing. Why did we make that decision? The decision has to do with different bending machines. Some companies have different benders, like our presses out there that we use for the sheet metal to make our machine. We have two different high precision presses that produce different bends for the exact same K factor and the exact same material. Now, the reason that happens is the tooling of the part that's actually making of the bend is slightly different. So we're also going to have a slightly different radius of the finished sheet metal bend. We check on the inside out there, and we're going on sheet metal, you'll do it on the inside of the bend. On tubing and square tubing bent, you're going to check at the middle of the tubing, not the inside, not the outside. But on sheet metal, you're checking from the inside, and it would be off a little bit. So across the two different machines, which meant if we automatically changed your K factor to what you just measured or what you want to do, then here comes the next guy comes along. He wants to use the program to generate a bend for the other bender. It is now wrong because you changed his K factor. So typically when you do K factors, they are specific to a machine. So if we're using, let's just say, a JD squared bender, it's going to may bend at a certain point, and then we switched over to another manufacturer's bender. He may have a square die, for instance, that has a slightly different profile on the bottom that may either exaggerate or diminish the effect of stretching the tubing. You know, and we've looked for years for one that kind of diminished that effect as much as possible. But at a certain point in time, you got to call it a day, and that's the number you're going to live with. So we know it's wrong. So we've checked it, nothing changed. So how are we going to change our part to get to our correct K factor? We're going to go to edit the frame again, and we are going to modify the profile. Now, here's the profile right here that we've just got selected, and we're going to select it again because when we originally selected that profile, the K-factor was 0.5, so let's select the active profile. See how it's 0.33? We're going to select or close and make that active. Now, everything's in red. We need to click right here in the bottom right, apply to the selected tubes. Okay. Nothing changed, right? You didn't see anything changed. It's because it didn't change the part. We changed the calculation. That's going to calculate how much did the doggone tubing stretch so that we could determine how long of a piece of material do we need to cut to make this part. So now let's go ahead and apply and close. Go back to bin selected tube. Look what we've got. 66.38 inches. So if I grab my little calculator right here, and it was 67.17 minus, move this over, 66.58, 66.38, enter, 0.79 inches of that piece of tube is too long because, so if we cut this tube and we bend this part, let's go ahead and, let's just go ahead and apply and close. This part here is going to be too wide and too tall because we had the K-factor wrong. So by getting to the correct K-factor, we bring that down closer and closer. Okay, so let me show you an app that is in this software right here that is going to let you determine what the K-factor should be. Okay, I've had a little bit of change of heart. I've gone back into Inventor so that I could show you a little bit more detail about what we're talking about. I think I could clear some things up here if you're still a little bit confused. So what I did is I drew real quick a 2-inch by 2-inch angle here that we are going to bend as a piece of sheet metal. Now for this segment of the video of the K-factor, I'm going to be talking about sheet metal. Even though we don't make sheet metal press brakes, we make tube benders. We're going to talk about sheet metal for a minute because this video is about K-factors. Let's go ahead and select our metal in Inventor. We're going to go with 12 gauge steel. If I click the edit button on the unfold rule, it's going to show a K-factor of 0.3639. Help me remember that number. Let's get out of here. 3639. Let's go ahead and cancel. Now, what we're going to do is we're going to create a contour flange. I don't want to bend from one side. I could, it don't matter. I want it in the middle. Now, if you notice, we got a blue line there, and that's telling us where we're taking our measurement from. The top of the flange to the inside of the bend. You can see it pretty good right here. Now, if I change though, if I go to the outside of the bend, that's what we want. Notice this whole piece got shorter. So if I was to go to the outside, I incorrectly selected that, let's just say, and I say okay, and then I say create me a flat pattern. Let's measure it. 4.016 inches. Well, there's no way that's going to be right because I told you earlier the metal's always going to stretch. I can't imagine it not stretching. Let's go back to our folded pattern. Let's edit what we just did right there. We're going to go to the contour flange and we're going to edit it. There we go. This time, let's select the other side. This is the side that we want to... Did I do it? I think I did it. Let's see. Yeah, no, I didn't do it. There we go. I'm sorry. Okay, this is the side we want. Now look what happens when we go to measure it. 3.81. That's over a 200 thou difference, 0.2 of an inch, or 5 millimeters, just because we changed which side we were measuring on. I'm just showing you that because, believe it or not, it has happened here. Okay, so you always want to do your profile in your CAD program outside leg to outside leg. Okay, now let's go ahead. We have cut ourselves a billet as a standard here at JD Squared. We cut them at 2 inches wide, 4 inches long. So we go out and we make our bend and we measure it. One side's going to be correct. Should be correct. Is it going to be correct? Well, it doesn't matter if it is or it isn't. We're going to measure both legs, and then we're going to take that difference, and we are going to apply it we're going to make changes to our K-factor until the new billet, instead of being 4 inches, is that length that we have calculated we need. So let's go through that process real quick, because I don't know if I explained that clear enough. We have a piece of metal here that should be 2 inches tall, 2 inches wide. We measured it, and we measured it at 2.1 inches tall. No, I don't want to use that number. We measured it at, 2.1 inches tall by 2.1 inches wide, So we're 200 thousandths of an inch too wide. If we go to our flat pattern and we measure, I'm sorry, hit the wrong button. We measure here, we get 3.81. We need to change that number, because if we're 2.1, this particular number here is going to have to get smaller if we want to get to the right deal. So what we would do is we would go back to our sheet metal, and we would literally, you're going to love this, we are going to change this K-factor to another number, go back, check it again, and see if it's at that calculated number. The 4 inches long minus the amount that we measured that we were too tall and too wide by. Adding those two numbers together, we're going to change that K-factor. Then we're going to go back over here, and we're going to, in fact, let me show you here real quick. I think Inventor's going to let me do this without screwing things up too bad. All right, 0.3639, let's just change it to 0.3 and say save. And this works in all CAD programs. This isn't just nothing special here. I think you might have just saw it got smaller, right? 3.801. That's a weird number. I'm kind of shocked it only changed that much. But let's go back to, but it did change. Let's go back to our sheet metal defaults. Change it back to, come on, 3639, and say save and close. And we're going to cancel it. Let's measure it again. It should be 801? No. So it changed it about 11 thousandths of an inch, 3.8108. So it doesn't have that pronounced effect. But remember, we're dealing with a piece of metal that's only 1/10 of an inch thick. All right, now let's go back to the flat part. That's how you would do sheet metal. We simplified that at JD Squared. And by the way, if you have a press brake and you have our program, you could use it to do what you're trying to do, to calculate it. But let's go and see what we need to do in our program to get this number correct. Okay, let's finish up this video by me now showing you how to use the KFactor calculator. I went over here to create frame, and I clicked on profile library, brought it up right here. Here's our 1.5 inch tubing that we're working with in this particular example. And we have a K-factor of 0.33. We are going to calculate, let's just say it was 0.5, right? And we want to calculate it. So we're going to click calculate K-factor. It's going to bring up our calculator. And what we're going to do is we're going to go out there, we're going to cut a piece of 1.5 inch square tube, whatever, to a certain length. Let's just say 24 inches. By the way, that's a good length. That's a good test length, but it could be anything. But we're going to go with there. We're going to say the outside diameter of the tube, even though we're dealing with square, doesn't matter. It's 1.5 inches. We should probably put a little thing over there, or width. The center line, remember we talked about center line radius? We got to know what that is. And we have said that our center line radius is 5.625 right here. We're going to put that number here. What we're going to do is we're going to go to our tube bender, and we are going to bend it, this piece of tube, as close to 90 degrees as we can possibly get it. We want it eyeball, damn near perfect. Then we're going to measure leg 1, this leg right here. Let's just say we measure it, and it comes out to 12.5 inches tall. Now we're going to go and measure the other leg, L2. It comes out at 12.25 inches long. I don't know if this is right or wrong, but you get the idea. All right, I hit calculate. The K-factor is red, 1.843. The reason it's red is because it's an impossible number. So since I just guessed at a number, I guessed at a bad number. Let's go to 7.5 and see. We're looking for green, red, 24 inches. Let's go. Let's see. Calculate. Red. We're getting closer, guys. Let's go 16 inches. Okay, now we're green. So Camelot has said this is probably a valid K-factor. I'm going to let you get away with it. So we're going to say green, but that's 0.251. Is it the 0.33 that we know what we're looking for? Not a big deal. Now, if I'm happy with this number, if I've measured all this correctly and I've got the right centerline radius, that should be the correct K-factor. Let's go ahead, okay, take it over to calculated values. You can see right here it is now filled in. All you got to do now is hit the save button. From that point on, that's what's going to be happening. We're not going to hit save. We're going to go back to 0.33, then we're going to hit save, even though I don't probably have to. Anyway, that, believe it or not, is about everything that I could think of telling you about K-factors. It is, it's little black magic doing bending because you're dealing with different hardnesses of material. Bottom line is, don't expect perfection. If you need to pretend you're working in a grenade factory, because whenever you go to bend anything, you're not going to bend perfect 90s. You're not going to have perfectly heat-treated metal. You're not even going to have perfect thicknesses. If you get a piece of square tubing that, for instance, that's got a welded seam on it and it bulges up on that one side, even that could affect it a slight amount. So anyway, that's all I know about K-factors, and I hope I've got you on the right path. Appreciate you checking in, and I hope to see you later. Bye-bye.